exponential, and other transcendental functions. Does that sound scary? You hate logs? Look at it, you're already going into it with a negative attitude. Maybe this would be better logs. You use sport the bow tie. Very nice.
Thank you.
Wait, what happened to the suit? Were you wearing suits?
I took the suit off.
Why?
Why?
I don't want to wear a suit all day.
That's true.
Why are you wearing a suit in the first?
Yeah.
Why not?
Well, then why? I don't know why.
Suit up.
I had an
Suit
interview.
up. What do you think?
Fancy.
Wait, ass up? Suit up.
Do you?
Straight up.
What's that from?
No.
Oh, I
You know what?
Your Christmas. Go watch these.
What's that? Was it your
No.
My Christmas suit?
Go
That
away.
I had this morning?
You should have
No.
worn that to the interview.
Christmas suit? No, I got a better one. I got a Batman suit.
Oh, that's sick.
Hold up. When you say Batman, is it a suit with Batman
Not
logo?
It's a suit. It's a suit covered in Batman logo. A regular black suit.
Do you have a
It's got
collar?
logos all over it.
Do you also have like an actual Batman suit?
No. That would be kind of weird, wouldn't it?
Buy you an adult onesie.
You mean like a cowl and a cape and a utility belt? No, I don't. I just have a suit with Batman symbols
End
on
of the
it.
year gifts. Why don't you just get the utility belt?
Yeah.
We're having a full discussion.
I was thinking like that.
Show, you want to show reading the book?
Hey everybody, it's Cuba.
Caitlin talked to Batman. Because he emailed me.
I don't know. She's coming home today. I'll talk to her about it. She's got a lot going on right now.
Just have her, it'd be good to get an email because she talked to us.
Again, I would imagine so, because they're in the middle of rush. So.
It'd be good to send an email to Pat this week. He emailed me because he's putting his schedule together and just wants to help.
Oh, I saw the movie. It's pretty good.
Thanks.
Remember my mom read
Yes, sir.
So, I just have a
About the, I can't hear you.
like 2 years
The
ago.
Christmas suit.
Yeah, I saw
Yes.
that in the
Well, it's a holiday suit.
2009 was
Yeah, alright. So,
Well,
I
what's the
saw
difference?
I saw him in the
There's no manger on my suit.
Did you buy it for the store? Did you order it?
No, I ordered it online.
Did you custom fit it?
This one is
Yes.
Okay, that's what I
I
said.
didn't know why.
What if it doesn't fit?
Yeah,
Well, it
2009,
comes in
2 years ago,
different sizes.
2011.
Yeah, but I have to go up a size.
I was like so sure that's not right. How do you know what year this is?
Right, I was like,
Going down my shoulders already.
The dude was like, yeah,
I know that.
Normally I
I don't
wear
know what year I
42,
was
but with these shoulders I'm up around 48.
because I was
When he's going. Usually I just wear pants as a jacket because that's the only thing those guns that fit.
Oh yeah. I have a 10 for like.
Yeah, I did the opposite thing. I had to get rid of all my suits because I lost all the weight.
Really?
Yeah, you can't because I looked like I was wearing a circus tent. I actually brought, sorry, I interrupted. I brought my suits in to get them tailored, and the tailor just went, no, not gonna happen. Couldn't buy any suits. Oh, sorry, guys.
You have Cubs shoes too.
Like a regular suit with Cubs logo all over.
It was like, no. It was
No, they have like the days
It's
where they
always
all
there.
dress up the same and
Yeah,
like there's a theme and one of them,
Yeah.
it was just one
every red light.
Those are shoes.
Crazy suits. Because I've seen a suit that's, it's a regular suit, like my holiday suit, but it's blue with logos all over it.
It wasn't blue. It was
Like
red.
pants.
It was like red, blue, and then pants. And then
Yeah, but that color suit you had today, that was 50 when I looked at that, and that's more expensive.
Thanks. Yeah, that was one of my new ones.
It's neat, right?
I am recording already. Okay, so as Dante has already mentioned, he doesn't like logs, but that's okay because well, that's not okay. You're gonna have to learn to love logs. So we're gonna talk about some logs, and in particular the natural log. We're gonna talk about E. Everybody know what E is? Yeah, don't. Find the derivatives of a function involving the logarithm. So you did logs in pre-calc and maybe advanced algebra, but now we're going to start taking the derivatives of logs. And then, of course, if we take the derivatives of logs, what are we going to do then? Antiderivatives. Okay? This will be fun, right? Let's take a breather. We'll do a nice, simple problem. You ready?
Oh, there's nothing funny.
Just solve that integral. Easy peasy. Gesundheit. Is that a clip on or did you type it? Okay. Yeah. I can't, I tried, I have one, I can't type. I never learned. It's hard. Yeah. Remember, it's a definite integral, so you should get a numerical value. What's the problem? Does anybody have it?
I think
I don't know.
No.
One.
One?
No.
One.
Zero.
Zero.
No.
1, 4?
Well, let me ask you this, what's the problem?
Hard.
It's,
X to the 0. X to the 0.
what is it?
Everything.
X to the 0.
Yeah, well, what's x to the 0?
1.
1. That's not the problem. What is the problem?
It's undefined.
You can't plug in like 4 and 1.
Zero.
That's not the problem.
The antiderivative is 1 over
This
0.
is a problem.
Bingo. So let's talk about the process for taking that antiderivative. That's x to the negative 1 power, correct?
Yeah.
And how do you take an antiderivative? Raise the power by 1, so that would be 0. Multiply by the reciprocal of that number. So as Dante mentioned, now all of a sudden we're multiplying by 1 over 0. That's a big no-no. So your reaction should have been, I can't do this. Everybody understand? Where is this desk? No, I always,
No, there's only one over there.
no, there's always 3 there.
There's three?
There's
two there.
We're missing
No,
a
there's
big, no,
always-
we're missing one of these big desks, those are little desks.
Wait.
Like, see how those little desks?
Those are
Those
big
are
desks. This is why we can't have that.
That's the first one.
It's kind of nice, I got some movement room back here. Okay, anyways, you can't do it. All right, so that's fine. From a mathematical approach, we can just say does not exist. But with what we know about integrals, that makes no sense. Why?
It's like, there should be a value area,
Why?
because it's on a graph, so if anything, it would be 0 if it's just like direct down.
Good, get out your calculators. Graph that function. You should know what that function looks like, but for those of you that don't, get a little refresher there. Graph 1 over x. And change your window to just go from like 0 to 5 and 0 to 5 on the x and y. We only need to see the first quadrant. Okay, so there's the graph. And as Maggie mentioned, this should cause a problem. The integral can't be solved because we get 1 over 0, which is bad. But from what we know about integrals, there should be an answer. Because you can see in the graph that there is area under that curve from 1 to 4. And that area is positive, so we should get an answer. Right? Good. Fn in that. See if you do in fact get an answer. See if the calculator is smarter than us. I'm going to guess it is. Oh, you don't have, okay, so you do the function. Comma.
It's going really well.
Comma 1, comma 3, close parentheses. All right, what do we got?
1.48.
All right, so we're all on the same page. We do get an answer, right?
Yeah.
Okay. So does that answer make sense? Well, if you look from 1 to 2, you've got, 3/4 of a square, and then you add a little bit. So that's a reasonable answer. So it begs the question, well, how do we do that then? Because mathematically we can't do that integral, but we should be able to do the integral. In fact, the calculator knows how to do the integral because it got a value. So what does the calculator know that we don't yet know? Natural log, correct. So that is a summary of what we just talked about, and so we get a definition. This is how the natural log is defined. It's defined as the area under the curve of the graph 1 over x from 1 to some value, or 1 over t from some value x. So we got that change of variable thing going on, you recall fundamental theorem of calculus business. That's where the natural log comes from. I don't think you ever discussed that in pre-calc or in advanced algebra. You just, hey, here's this cool thing called a natural log, go and do things with it. But nobody ever explained where it comes from, and now you know. You got a discussion topic for the dinner table tonight. Hey, Mom, do you know where the natural log comes from? Well, that's probably won't work for you, Mark, right? Mom's a bad teacher. Your mom, by the way. Ask her. That'll be the challenge. The big challenge for tonight. Anybody else's parents math teachers? Is he gonna be at the dinner table tonight?
I'll ask.
Right.
Which
Well, let's finish this one, then we'll finish.
I know.
All right, so there's a picture of the natural log function you may have forgotten. Passes through the point 1, 0. It's asymptotic to the y-axis. It's always positive, so you can't take the natural log of a number. You can't, sorry, I said that wrong. You can't take the natural log of a negative number. You'll get an error. Try it on your calculator, by the way. You got the ln button over there on the left. Take the natural log of -4, see what you get. The range is -infinity to infinity. So it keeps going downward forever, goes upward forever. It's 1 to 1. We don't really care about that. And it's concave down. That's some calculus talk. Always increasing, always concave down. This is some pre-calc stuff. Sure. Okay, so before we move on, let's look at something interesting. Let's look at this point right here, the point 1, 0. And relate that to, we'll talk calculus now. Why is that 0? Well, if I go back a slide and I look at this, what happens if x is 1? Yeah, anytime you take the integral from 1 to 1, you're going to get a value of 0. If I move to the left then, or sorry, that's the right, go to the right, that number's going to continue to get bigger and bigger. And then we got that little business in there that we can talk about later. Why do you get a negative area there? Well, look at the integral again. What if I put in 1/2 up there? What's wrong with putting 1/2 in for x? Why? Who's talking? Michael?
Because it's flipped around, it's less.
Good. So remember, when the top limit of integration is smaller than the bottom, you got to flip it over and put a minus sign in front, which justifies why this would have negative area over here between 0 and 1. Okay, good. So take a break from calculus for a second, step back to the pre-calc, which Dante loves, all your log properties. We talked about this one already. Number 1, the natural log of 1 is 0. The natural log of a product is the sum of the natural logs. This is why people are bothered by logs, because it doesn't follow logic. But we've had experience with that already, because when we did the product rule for derivatives, the product rule had a plus in it. Quotient rule had a minus in it. Kind of true with logs also. So the log of a product is the sum of the logs. The quotient sorry, the log of a quotient is the difference of the logs. And then if you're taking the natural log of an exponent, you can move the exponent out in front where it's not going to harm anybody. Okay, so let's do a little bit more pre-calc just to make sure you know you got everything under control. If you're using your calculator, it's easy. The calculator can take the natural log of 10/9, but if you don't have a calculator, you may have to break it into separate parts. This is not the most practical thing for us right now. However, when we start taking derivatives, you're going to want to be able to break natural logs into smaller components that you can work with more easily. No problem. So rewrote that as a power to the 1/2. What can I do next?
Move that.
Good, move the 1/2 out in front. So I would have 1/2 times the natural log of 3 plus 2. Now what? So 1/2 times the quantity natural log of 3x plus the natural log of 2, correct? No, I tricked you. You can't do that. It's only products that you can break up into sums. That you have to leave as is. You cannot distribute the natural log to each of those terms. It doesn't work that way. Think of the natural log like a trig function. Yes, sir?
I'm just confused on where you got the root 3x plus 2. Or is it a separate problem?
Separate problem.
Oh, okay.
Yeah, problem A, problem B. Yeah, that would be very
That
confusing.
makes sense now.
Yeah, how did you turn 10/9 into the square root of 3x plus 2?
Yeah, it was.
That would be some math magic. And then part C. Different than part A. Part A was just a quotient that I split up into a difference, but there's another step for part C. Because that first term is a product, I can break that product into a sum and end up with that bad boy. And that's about as easy as you can get. But again, that's pre-calc, and we don't really care about pre-calc. We want to do some calculus. Calculus is much more fun. Are we good? Any problems with that? Not only should you be able to do problems like I just did there, but you should also be able to go backwards. If I give you the answer to problem C, you should be able to put that puppy back together to look like the original question for part C. You practice a little bit of that tonight, or over the weekend, or Sunday night, or Monday morning, 5 minutes before fourth period. Let's talk about E. No cheating with the calculators. Does anybody know what E is? Go. Keep going. That's all you got, 2.7. It's not a 2.17. 2.7. But I got a good way for you to remember it. This is really cool. It's not a song, I don't sing. Who's got a $20 bill? I'm just gonna borrow it, I'll give it back. I need a $20 bill. Mike, you got a $20 bill? This is awesome. You will never be able to forget about the number E ever again after seeing this.
I'm charging interest.
I understand. Okay. Here's E using a $20 bill. You ready for this? My hands free. Here, hold that. See that button right there? You're gonna click to the right when I give you the
I got you.
So this is a $20 bill. $20 bill. Who's on the $20 bill? It says right there. Andrew Jackson. What is he famous for? Wow. I don't know how that's going to help us find E, but I was looking more for.
I don't know anything else.
Set the precedent for most vetoes.
I'm sorry, what?
Set a precedent for using a presidential veto.
Seventh president.
Trail of Tears.
I'm sorry, what was that, Ben?
Seventh president.
7th President of these United States of America. 7th President of the United States of America. All right, Ben, do you know when he was elected?
Nope.
Guess.
18 something.
18 something is good. You're within 100.
1820.
1820. 18, good. You know, he was president 2 terms, right? Right. Shh. Now, using my vast stores of origami skills, I can fold this $20 bill into a football. Into a bird. When I'm done folding, I get this, which from a geometric standpoint is what? What kind of triangle? What kind of right triangle? What kind of isosceles triangle? Right isosceles. Good. Also known as? Is that you, Mark? Say it loud, say it proud. 45, 45, 45, 45, 90. Wouldn't that be weird?
You had it.
This is a stretch.
45, 90,
No way I'm
45.
remembering this at all.
What are you talking about? $20 bill, 7th president, 1828, 1828, 45, 90, 45. Boom.
2.
All right, find the E button on, thank you. Let me relinquish your control. Find the E button on your calculator and pull that up to see how close we are. Now the calculator, I think, will tell
It
you
cuts off after the second 18.
here, 6.
No. Where's
This
the
8?
Yeah.
Where's this?
Mine says.
Wait, hold on. Anybody not find the E button?
Second, and then the dividing line. Oh, the divide
Okay,
line.
got it?
Second divide.
Good. So now we know that we have this letter E, which is actually a number. That's the big thing you got to remember. What's the derivative of E? 0.
Boom.
Why?
It's a number.
It's a number. It's a constant. What's the integral of E?
EX.
Good. Okay. But again, you got to remember it's a number. It's just like pi. So if I ask you to take the derivative of E squared, don't tell me it's 2E. It's 0. And of course, there's what E is. But where does E come from? Does anybody know? I would be worried if you did know, because that would be really nerdy. Okay, so we're going to take the same idea that we talked about with the natural log and tweak it a little bit. You broke my clicker.
Mary.
Mary! Mary!
Good one job.
Give it back to her, Steve. You gotta do the.
Can't give it away.
You didn't give her the signal.
Oh, yeah.
Oh, that's right.
Yeah. Ready?
Oh man, if that
Would that have been awesome if it would work?
Wait, maybe it's another one.
Are you just pressing every button?
Yeah. I got nothing.
He's gonna be
Oh,
so
did you want to see the light flashing up there?
What if it's just like this freaking out?
Don't
Switch.
give me
Maybe you fixed it.
Oh, it worked!
Yeah. Yeah, it worked. Here's how E is defined. E, it's a little hard to see because it didn't show up. That region is pink. Okay.
There's no.
E is the value that you come out to guarantee that the. Where's my pen? Hold on. Trying to write with the clicker. Oh, boy. E is the distance that you come out along the x-axis to guarantee that this region Mary broke my pen too? Has it?
Wait, here comes circle again.
Has an air.
Maybe the clicker works now.
I'm not gonna try it because if it does, I'll feel silly. E is the distance that you come out to away from 1 to guarantee that that area under the curve is 1. Okay. How did they find that? I have no idea.
They guessed.
Yeah, they they guessed and checked out to like 12 decimal places. Uh-huh.
Well, they plugged it into their calculator.
And then somebody said, wasn't Hamilton the 7th president of the United States? Yeah, he was elected in 1828, right?
Wrong president.
That was
Jackson.
Jackson, sorry. Sorry. Hamilton wasn't a president, he just got shot.
This theory's gonna go to crap when the new $20 bill comes out.
Yeah,
Harry Tubman. Harry Tubman.
Oh, is it the 20 that I thought it was the 10.
Yeah.
It's the 20.
Wait,
Wait,
you better be stocking up on your $20 bills.
Yeah.
Jackson.
Yeah, otherwise this is gonna work. Unless
Just keep an old one.
unless she had 7 kids. And those 7 kids had 18 different jobs by the time they were 28. And they got fired and got hired at 18 more jobs.
She was
45, she died when she was
90, and then.
How old was she? when she died?
90.
Was she really?
Don't know.
Oh, that would be awesome.
You can still be
Hold
on.
up the dollar for 45.
I'm not sure. Oh, yeah, you're right. That'd be probably better.
Mary, you broke my pen now.
$1 bill, anyone got one? Huh? I said I could do anything with 100.
I don't know what you want me to do.
Make the clicker work.
You're welcome.
You're
You're welcome.
Good job. All right, so here it is summarized. The natural log of e is the integral. So what I did is I took that first theorem that we had about the natural log of x and changed the x's into e's. And so the natural log of e is 1. In pre-calc, you approach that a different way. You said you did log, 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 log base 2, log base 5, log base 7, log base a million. And you learned about changing log forms and everything else. And then you said, oh, let's stick this weird thing in there in e. So we'll do a log base e. But we're not going to call it log base e. We're going to call it natural log. We're going to give it its own name. And then when you take the log base e of e, you get to 1. No calculus involved. Pregunta?
Why is it called, why E? Like, when they discovered it, they just, instead of saying like ooh, like why E? I'm confused.
I am too. I don't know the answer to that question. I could just make something up.
What should we call it?
I'm sure.
Oh, God.
Go ahead.
Make it make Jackson.
Say again.
What should we call it?
That's good. Yeah, originally it was EH, but they dropped the H because it was too complicated. Right. Awesome. Okay, so that's why if I did this, you could probably come up with that because you could use the pre-calc that you already know. Log base E of E is going to be 1. Log base 10 of 10 is 1. Log base a gabillion of a gabillion is 1. Then we throw the calculus part in there to explain why that becomes 1. Are we good? Awesome. So, use your calculator. You may have done this already, but make sure your calculator is working. By the way, logs don't care if you're in radian or degrees. So, if your calculator isn't doing this correctly, it's time for a new calculator. But we talked about these answers. Notice what's happening. We start with log of 2. We get an answer smaller than 1 because we know that e is 2.7. So if we go to the left of 2.7 between 1 and e, you're going to get a value less than 1. Now all of a sudden we shoot way to the right and take the log of 32. We're going to get an answer bigger than 1 because, again, we're adding on to that area of 1. And then we already talked about this. What happens when you take the natural log of 1/10 or 0.1? It would be negative because we're talking about a negative area. Or you would have the limits of integration reversed, so you'd have to flip them over, stick a minus sign in front. Okie doke. So let's take the derivative then. So we talked about integrals to get definitions. Now we start talking about how to actually take the derivative of the natural log. There's the definition. Not definition, but that's what we're going to use. It makes sense. I just went backwards. I took the definition we had in the previous slides. I took the derivative of both sides. So if the natural log is defined as the integral from 1 to x of 1 over t, if I take the derivative of both sides, fundamental theorem of calculus, it becomes 1 over x. You can forget about 1. 2 is what we're going to use. This puppy right there will solve any natural log derivative problem. You have to burn that into your brain. U prime over u. U prime over u. U prime over u. Derivative of a natural log, u prime over u.
So then u is greater than 0 for the second one?
Yes, because you can't take the natural log of a negative number. Even if you do this, u prime over u. Okay, what's a derivative of x? You should have all said 1.
One.
Good, good. Because what's the derivative of x?
1.
1. And what's u in this case? X. 1 over x. Done. Okay, u prime over u. What is it? Good. All right, what's that derivative? Patrick.
1 over 2x.
Nope.
No.
What's u?
Oh, use 2x.
Good. So what's u prime?
2 over 2x.
Which is?
Just 1 over x.
Good. Easy, right? Yeah. U prime over u. Madden, your turn.
U is x squared plus 1.
Uh-huh.
And u prime is 2x.
Uh-huh.
And then it's 2x over x squared plus 1.
Can you simplify that? Because you just cancel the x's, right?
No.
Good. I'm just gonna have Barry hit you if you answered that incorrectly.
She break me. She breaks.
Yeah, she's good at breaking.
Oh,
But then she
right.
magically fixes it.
Yeah.
So she somehow magically fixes it. Product rule. Quit your whining. It's just a product rule, but again, the u prime over u only applies to the natural log portion of it. So notice I wrote out the whole thing, but we're way beyond this. But just, you know, in case you needed a refresher because it's been a while since we did derivatives, we would get this, and then it simplifies to that. Okay, first times the derivative of the second. Well, the derivative of the second is the natural log, u prime over u. Then the second is natural log times the derivative of x, which you should all know by now is just 1. Easy, right? Don't make this more difficult than it has to be. Just remember, u prime over u. It'll get you very far, as will and but nor. Right, Schoolhouse Rock. Are you guys too young for Schoolhouse Rock?
No.
You know Schoolhouse Rock? And but nor will get you pretty far.
I didn't watch
Which is kind of weird because or doesn't really rhyme with far, but they sold it that way anyways.
it. It makes money.
They made a lot of money.
Sure they did.
Yeah. This one gets a little weird. It's a chain rule. So we have a function within a function. Bring the 3 down in front, reduce the power by 1, because remember we're taking derivatives now, so we're subtracting from the exponents. Chain on the derivative of the inside function. And by now, you should have had it burned into your brain that the derivative of the natural log of x is just 1 over x. And we get that. On a sidebar, you need to be careful when working with the natural log to make sure that you understand the difference between this and this. Do you all understand that? What's being squared in the first one? Yes, what's being squared in the second one? The whole thing. This makes no sense. It's not like trig where you write the 2 in there. Don't do that. But if you intend to square the whole thing, make sure you put it in parentheses. Oh, the pen's working again too. Good job, Mary.
Thanks.
But now the clicker stopped. Oh no, there we go. Okay. So now, nobody?
It's a taste.
Overwatch.
Yeah.
Have you Overwatch player? Nobody?
A little bit.
Dabble.
Dabble a little bit. Everyone's doing it.
I understand that. So we got another weapon in your arsenal. That's why that's there. This is kind of ugly, but it's a method for taking derivatives using logarithmic. It's called logarithmic differentiation. It involves logs. So you want to take the derivative of that bad boy. You can't simplify it algebraically. You got a quotient. So we're going to dive in and do a quotient rule. The problem is you've got a quotient rule with a chain rule up on top, a chain rule on the bottom, and it's just a recipe for destruction. So we can use something called logarithmic differentiation. Step 1, take the natural log of both sides of the equation. I'll give you the steps first and then we'll work through this problem. Step 2, apply logarithmic properties to simplify that thing. Step 3, oh, sorry, and differentiate, and then step 3, solve for y prime. And what you're left with is the derivative. This will be fun. And it'll make a little more sense when you see it in action. Now, how do you know to do this? What I've seen in the past is I teach people this technique, and then they start logarithmically differentiating everything. Don't do that. Okay, it's not an easy method to use, and there's other techniques that you could use that you've learned and practiced already. How will you know when to logarithmically differentiate? Because it will say logarithmically differentiate the following function. Okay, got all 3 down? Ready?
Is it solve for y prime?
Solve for y prime, correct. Hopefully the pen's working.
Oh, can we look at it, it's just like the orders.
Okay, I think we're good. Yes. Okay. Step 1, take the natural log of both sides. Step 2, use your logarithm properties. I'm going to leave this side alone. So since I'm leaving it alone, I'm just going to write equals. How do I handle the log of a quotient? Subtract. So this becomes the natural log of x minus 2 quantity squared minus the natural log of the square root of x squared plus 1. Continuing on, I could, well, what can I do with the first part? What can I do with that guy?
Bring the 2 out.
Sorry?
Bring the 2 out in front.
Bring the 2 out in front. We'll see if that helps us. Okay, we're done with that guy. What about this one? Second part. Bring the 1/2 out in front. Okay, make sure you keep that in parentheses so we know we're taking the natural log up. So step 2 was use logarithm properties, and then what?
Differentiate.
Right. Differentiate implicitly. So we'll put this back. Let's see how this goes. What's the derivative of the natural log of y? 1 over y, y prime, because we're differentiating implicitly. 1 over y, y prime. Ooh, there's a y prime. That's good. Okay. What's a derivative of 2 times the natural log of x times quantity x minus 2? What should you be thinking right now? U prime over u. What's u prime? 1. What's u? X minus 2. So we'll put a 2 up on top. All done. Okay, that's what I mean. Don't get bogged down in this. Just remember u prime over u. That's an easy...
Do we multiply it by 2?
I did. That's why the 2's up on top. All right. What's the derivative of the second part then?
2.
I'll leave the 1/2 there. What's the derivative of the natural log of x squared plus 1? What's u?
2x.
U is x squared plus 1, so we'll put that on the bottom. What's du? Sorry, what's u prime? 2x. And no canceling there. Leave it alone. Oh, I could cancel here, though. Whoosh, whoosh. Last step. Solve for y prime. How do I solve for y prime?
Multiply y to 1.
Multiply y by both sides, or move y to the other side. But we know what y is. What's y? That mess that we started with. So this bad boy becomes 2 over x minus 2 minus x over x squared plus 1. All of that times x minus 2 squared over the square root of x squared plus 1. And now simplify that. I'm just kidding. You don't have to simplify. It was a math joke. I have to simplify because it's so ugly.
So then why were we told that x can't equal 2 at the beginning of this problem?
Oh, because you'd be taking a natural log of a value of 0, which 0 or negatives don't work.
So we're at
So when we originally started, we started by taking the natural log of the function,
Right.
which for the most part is okay, unless that function would give us a negative value or 0, which we can't take the natural log of, so it would negate the problem. So a lot of times when you do logarithmic differentiation, they're going to put a stipulation there that says, yeah, this will work as long as x isn't blah, blah, blah. Because again, if I put in 2 there, I get a denominator or a numerator of 0, and you can't take the natural log of 0. It's undefined. Okay? Like I said, not an easy approach, but it gets the job done. And I would argue that as tricky as that is, it's still going to be easier than doing a quotient rule with 2 chain rules wrapped up inside of it. Okay. But if you did do that, okay, so you get to the test and you forget logarithmic differentiation and you have 3 pieces of paper, you could work that through the other way and you'll get an answer that would be the same value. It might look differently, but it would still be the same answer. Okay? Any problems? 3 simple steps. Natural log of both sides, differentiate, solve for y prime. And then don't forget I subbed in for y because I know what y is from the problem that we started. Can I erase this? We'll go through this real quick. Working with absolute values, it doesn't affect the problem. Why doesn't the absolute value affect the problem?
Because it doesn't work with the negative value.
Correct. So by taking the absolute value, it guarantees you're going to get a positive value, which is still going to give you u prime over u. That's why u prime over u is so great, because it works all the time. Okay, no, okay, you know, no big deal. All right, we're done. No trigger, no, we save that for later. We just want to do logs today. Yes, sir.
How am I?
What's that?
My money.
Somebody bought
My
Oh, yeah, I forgot. Sorry about that. You know, I got caught up in the heat of the lesson. Yeah, those are natural logs.
I didn't know if it was good.
I like it.
No, no.
But what-
Anybody else? We're good on this, right?
Yeah.
Right.
think
Yeah,
artificial-
Twigs, good, exactly, right. My nickname in high school, Twigs, so I thought I'd throw it out there.
What are unnatural logs? Like artificial logs?
Yeah, like things,
So
some
what's
people
made
have
out
a
of
fireplace that
plastic?
never burn.